I did a little bit of digging to produce a short introduction. So Tom grew up in London with a burgeoning interest in science, and probably not from a sort of traditional background route of having gone into that form of vocation. But after A-levels, he went on to study chemistry at Sussex University, where I had no doubt he drew inspiration from members of staff, which included Professor Harry Kroto, the Nobel Chemistry Laureate at the time. And then Tom moved to join Imperial College, the chemistry department there, in 1993 as a fellow. And then he made quite fast progress through senior lectureship and was made professor in 2004. Tom then, as probably all professors do, moved, well, not moved, but took on a whole load of other roles: exams officer, director of undergraduate studies, and then led the department between 2007 and 2014. And it was during this time that I think he instituted quite a number of changes, most notably promoting gender equality. And I'm sure others might want to ask him about that after the presentation. He's invested keenly in careers of students and early stage researchers, and that obviously partly stems from his concern about watching the widening social inequality, and never has this year perhaps exacerbated that as much. Now, when the role of Dean of the Faculty of Natural Sciences came up, obviously, and I quote him here, he saw this as an opportunity to write some of the things I've just talked about onto a larger canvas, and I think that sums up Tom to a T. He was awarded an OBE for his services to diversity in education, amongst other things, in 2017, and whilst his term of Dean ended last year, it was just in time for him to take up his position as president of the Royal Society of Chemistry halfway through this year, obviously maintaining his role within Imperial College. So on a more technical basis, then obviously an expert in sustainable solvents, Tom's research has focused on studying the separate processes involved in chemical reactions, and in particular ionic liquids and the power that they possess. So if you like, chemicals that provide some sort of hope of replacing solvents used to dissolve materials, but that are obviously less harmful or hazardous to health and the environment. And as well as studying how they behave, he works on the practical applications of these solvents, and I think he'll allude to some of that today, such as dissolving textiles and plastics so they're more easily recyclable, and even dissolving wood to create biofuels. So why did we think about Tom for what is actually I think the first GC Christmas lecture, and I think we will make this a feature going forwards. But the Government Chemist Annual Review last year featured a keynote article on current issues facing the types of recycled materials being used for food packaging and resulting post-consumer waste chemicals. And there was a call for action, if you like, within that, which related to protection of the environment. And of course, the current discussions today around global sustainable development fits nicely into that, and indeed to Tom's expertise. So it gives me great pleasure to ask Tom to present the first Government Chemist Christmas lecture around the role of sustainable chemistry and its role in achieving some of the global sustainable development goals. Thank you, Tom.
Oh, thank you, Julian, for that kind introduction. I should say, you know, the meeting of Harry Kroto was, you know, just an amazing, you know, moment in my life. So I met Harry not at the time that he had the Nobel Prize, but at the time that he was doing the work which led to him to get the Nobel Prize. And he was my physical chemistry tutor for much of the time. And, you know, and we spent a lot of time not doing the tutorial problems and talking about the work that he was doing. And it was an amazing inspiration. And, you know, Harry is certainly one of those figures that I'm sure if I hadn't come across him, you know, ending up here would have been far less likely to have happened. And so, yeah, that Sussex experience. And, you know, and let me add, you know, Sussex was not my first choice university. My first choice university was Bristol. But unfortunately, I didn't get the A-level grades to go to Bristol because I missed my offer by just 1 point and ended up going to Sussex as my second choice. And God, that 1 point was the luckiest thing that ever happened to me in my life. And I will be, you know, eternally happy that I didn't quite make the A-level grades that I wanted in the first place. Well, anyway, let's have a chat about sustainable chemistry. And, you know, so the talk's in kind of two halves. So the first part is a little bit more about what the concept of sustainable chemistry is. And then the second part is a little bit more about, you know, some of the practicalities around it, particularly with regards to plastics, since they've become so much to the fore recently. Now, I mean, in a way, this is where it all started for me. And so this is the first time I was kind of aware at all of the negative impacts of chemicals in the environment. And in the 1960s, I was born in the early 1960s. In the 1960s, I do remember seeing on the news, I mean, obviously I was very young, but I do remember seeing on the news these pictures of foaming rivers that were causing problems. And, you know, and that foam came from non-biodegradable detergents. And the issue was that branch-chain alkyl benzene sulfonate detergents do not biodegrade, whereas the linear alkyl benzene sulfonate detergents do biodegrade. And nobody was, here in the UK, was trying to make non-biodegradable detergents, but unfortunately, the technology for separation of the starting materials that led to these wasn't sufficiently good. So even though, you know, most of the detergent in the packet or in the factory was in fact a linear alkyl benzene sulfonate, it was contaminated, if you like, by the non-biodegradable branched alkyl benzene sulfonate. And so, you know, people wanted to do something like this, but something needs to be done that could be done. And a lot of people have thought about the separation of the products. And, you know, this is quite typical, particularly when, you know, we think, oh, we've got, you know, this mixture of products that we have from our reaction. And then the last thing that we do is to try and separate those products in some purification process. And as much as that happens in the laboratory, that also is very much about how these things are considered in the factory. But here, the solution wasn't that. And the solution came from, you know, quite a different part of chemistry, which was, you know, there'd been growing interest in the mid 20th century in these materials called zeolites. And these are solid state materials that have these cage structures that get formed, which means that they have pores within them. And those pores, depending on which particular zeolite it is, are of very precise sizes, and that they can let some chemicals in and some not in because they don't fit in the pore. And these zeolites are often called molecular sieves. Well, what really came to the rescue here, and not in the separation of the product, as I said, it was actually in the separation of the stream of alkanes that were eventually going into these products. And so they allowed for the separation, or a particular one of them allowed for the separation of linear C10 to C14 alkanes from other oil fractions. And so you could get a very, very pure linear fraction. And then you do all the things you normally did. You would either do chlorination to make chloroalkanes or dehydrogenation to give alkenes. And those you could then use as alkylation agents, which then you could do the reactions, which eventually led to the alkyl benzene sulfonates. And so this is kind of, what we would think of as, the green chemists would talk about this, and the people who call themselves sustainable chemists would talk about this as a truly sustainable solution. Because it isn't about, you do the separation at the end, and actually what you end up with is, okay, you end up with your pure product, but you also end up with a pile of mess that you don't want, that you have to do something with. And this intervention far earlier in the process is what led to a truly sustainable solution. And indeed, now, and it gives me an opportunity to mention greenwashing, but all detergents sold in the UK are biodegradable because it's the law that they should be so. And so when we walk into our supermarket shelves and we see that, slightly more expensive brand X with biodegradable detergent written across it, the cheapest biodegradable, the cheapest detergent on those shelves is also biodegradable because the law says that it should be. And that's this thing that we call greenwashing, which is taking some green claim which is not justifiable or is not special, and turning it into a branding that then enables people to charge more, because we as consumers go in and say, oh, look, this is biodegradable, that's what I would want, so I'm going to use that one. As I say, when in fact the cheapest detergent on the shelf is also biodegradable. So now the kind of idea that I have of sustainable chemistry is, so we do know that in 1987, I'm just going to check that I haven't got my slides out of turn, because I might have done. No, I haven't. I've just skipped a slide. Okay, so I've just deleted a slide. So in the mid-1980s, Gro Brundtland produced a report for the UN, which was called Our Common Futures. And in that, she defined the concept of sustainable development to mean development that enabled us to meet our own needs without compromising the ability of future generations to meet their needs. And this idea really has taken a strong hold because of its, elegant simplicity. And so sustainable chemistry then becomes very straightforward. The implementation of that concept in the production and use of chemicals, and so that is broadly what we might call green chemistry. But it does also have this important and that's the application of chemistry and chemical products to enable that sustainable development to occur. But there are some problems. It may be simple and elegant, but there are some problems with this idea. And so here's a picture of St. Mark's Square in Vatican City in 2005, and you can see what it looks like. And then here is another picture taken at almost exactly the same place in 2013. And if I toggle between these two, you can very clearly see what the difference is, as suddenly by 2013, we have the bright lights of the screens of our smartphones and the other devices. So let's have a think about that. And so here is a fantastic representation of the elements that you will find inside a smartphone. And you can see, first of all, that there are so many of them, and varying from, absolutely the most common, like carbon, to some extraordinarily rare elements like neodymium and terbium. But what I want you to focus on are these three elements here, and they're indium, tin, and oxygen that together make up indium tin oxide. And indium tin oxide is the material that enables us to have our smartphone screens. It's a transparent material, so you can see through it and it makes a screen, but also it's conducting, which means that you can do the touching the screen to give an instruction. And so it's the material that has gone from, in 2008, frankly, except for a few academics, nobody cared about, to in 2013, it had become a material which was central to how we live our lives. And so here's a periodic table that you might not have seen before. It is a periodic table, just like any other, but it was produced by the European Chemical Society in 2019, the International Year of the Periodic Table, in order to show the abundance of different elements, and particularly the amount of the element in respect of how we are using it. The size of the element symbols give you the amount of that element in the Earth's crust. These are logarithmic representations, so twice the size is 10 times the amount. Otherwise, you'd just see a huge, great oxygen and nothing else. And the color coding is that we have green ones, which are, you know, a plentiful supply. The yellows are limited availability, perhaps some future risk to future supply. The ambers are a rising threat from increased use. And the reds are elements that are seriously under threat in the next 100 years. And there we find indium and tin, and particularly indium being one of those elements that is under serious threat, because suddenly it's become a material that we're using in huge, huge, huge amounts in our swipey screens. So indium is an element that, you know, back at the turn of the century would have been on here, probably green, because nobody really cared about it, into something that has moved to red. And so we find that we've got this inherent problem in this idea of not compromising the needs of future generations, because we don't know what the needs of future generations are going to be. We don't know what technologies they'll be using. We don't know what they are going to need. And so we do have this problem with that definition. So what people have moved on to is this idea. And so here are, well, the idea of sustainable development has moved on. Here are the sustainable development goals. There are 17 of them. Some of them are really quite technical, clean water and sanitation, for instance. Some of them are very societal, gender equality you can see here. And some of them are an interaction of both. Yet when I look at this, I can see in every single one of these, no matter how societal, chemistry and chemical sciences and chemical scientists have a contribution to make. And there is a fantastic article from earlier this year from David Cole-Hamilton at the University of St Andrews in Chemistry European Journal that really does look at this, and it looks at some of the individual development goals and how chemistry contributes. And so, for instance, you know, if you think about zero hunger and you see the, well, actually, the ammonia-based, nitrogen-based fertilizers that are so common nowadays are what has enabled the population growth that we have seen over the last decade and is responsible for feeding much of the world. Yet, we also know that there is a problem of the runoff of these fertilizers into local environments, causing things like algal blooms in river deltas and the like. And so that although there are solutions that have been chemical that have led to problems, and then of course that leads to the need to do research in order to solve those problems and things, for instance, that it's not necessarily a matter of saying, oh, what we need to do is change what the fertilizer is. It might be that what we need to do is to provide formulations that mean that we have a much more precise delivery of the right amount of fertilizer to the right leaf so that there isn't excess runoff. And so huge research challenges that come from looking at these different development goals. So now, like I said, the idea of sustainable development is very much the application of chemistry and chemical products to achieve the sustainable development goals. But in so doing, we need to use less stuff, and I like this. This comes from my colleague István Horváth, and his idea is rather than to think about this in just fold amounts, but to think about it like you would the rate of reaction. And so to use less stuff, which means to consume nature's resources at a rate that is lower than that at which they can be replenished, and so they will be replenished and we will be sustainable in that sense. But also we need to make less waste, which is to produce waste at a rate which is less than that at which it can be naturally remediated. And if it can be naturally remediated, then the waste will be dealt with by the environment. Now I'm going to turn to plastics, and because plastics are everywhere, and of course I think some of these pictures are directly from the Blue Planet, and plastics have come very much to the public's attention recently since an episode of the Blue Planet where people saw that plastics are absolutely everywhere under the sea and can have devastating effects on the environment and on wildlife. And they really are everywhere. And so if you look at this map on the left-hand side, and there's an indicator in the middle of the Pacific Ocean there. So that's a place called Henderson Island. It's one of the 10 islands. And it is as far away from large-scale human habitation as you can possibly be. And yet, the photographs on the right-hand side show you the plastics strewn across its beaches. And this study in 2017 shows nearly 38 million items weighing nearly 18 tons of plastics on Henderson Island's beaches. So plastics are everywhere. But the reason for that is because they are everywhere. And the pie chart here is telling you the mass of material that comes from petrochemical production that is not fuel. So the materials that lead to all of the products that you see on the right-hand side, all of those plastic products that we see around, I'm sitting in my kitchen at the moment, and I can see lots and lots of plastics in this room. So all of those products make up 80% of the mass of synthetic chemical production that we have. And so plastics really are everywhere, and this is why they're such a problem, because we use them in such huge, huge, huge amounts. And we often use them for things which are disposable. And this chart here is showing you in millions of metric tons an estimate of what's happened to all of the plastics that have ever been produced. So there's a primary production of 8.3 billion metric tons that have been produced. And of those, 2,500, 2.5 billion metric tons are still in use. And that's really important for us to remember. Plastics are used in very, very durable material, to make very durable materials, to make very durable products. And again, I say I'm in my kitchen, and I checked when I was looking at this, there is a cutlery tidier in one of my drawers, which is 30 years old. So I want that plastic to be durable. I don't want it to be disposable. Of those primary production, only 600 million metric tons have been recycled. And of that, only 100 million metric tons have been recycled twice. And so that's a tiny, tiny fraction. And the vast majority of the plastics that have been used have ended up being either discarded or, in slight preference, incinerated. And so again, this is why plastics are everywhere. They are used in massive amounts, and the vast majority of them are just discarded. So earlier this year, the RSC released a report on the sustainable use of plastics, because it's very easy to just say, well, we have to stop using plastics. And indeed, there are some things that perhaps we should stop plastics for. I have a particular bête noire of hydrogen-filled balloons, which not only, helium-filled balloons, which not only use up the precious gas helium, they also just strewn the environment with plastics. But, you know, who needs a plug-in air freshener, I ask you? And so we can reject and not use certain plastic products, but there are other plastic products that we need and we will be using into the future, and so we have to think about that a bit more. And here are the kind of major challenges that we identified. And so one, of course, is to understand the impact that different plastics have throughout their life cycles and understand where they are, where they end up, and how they behave in that environment. Plastics recycling, of course, is vital, and closed-loop plastics recycling is hugely important for us to be able to take those durable materials and perhaps recycle and reuse them, either as we do at the moment, which is largely mechanically, you know, things get popped up and heated and reformed, or chemically, actually broken down to the monomers that the plastic comes from, so that it can be repolymerized afterwards. And we need to develop far more effective closed-loop recycling. We need to understand and control plastic degradation in the environment, and I'll come back to that slightly towards the end. And the thing that I'm going to focus on here is we do need to develop new sustainable plastics. And here is a place from which many people expect those plastics to come, and that is, you know, as oil production becomes more and more expensive, as sources of oil become more and more difficult to access, then biomass is being looked at very much to replace those materials. And, you know, I've just kind of described to you the petrochemical refinery. And one of the things that's very interesting about petrochemical refinery is it would not be sensible to suck the oil out of the ground in the first place if it wasn't for the huge volumes that were achieved in fuel production and the use of fuel. However, very much of the value that comes out of a petrochemical refinery comes from about 4% of the mass, which are all those things that I had in that pie chart, which provides about 30% of the value of the material that comes out of an oil refinery. And so those two things kind of coexist and feed off of each other. You need the volumes in order to be getting the stuff out of the ground, but you need the money that comes from the higher value products in order to make it all worthwhile in the end. The integrated biorefinery has the same integration, but it just has as its carbon source biomass. And you need to think about the biomass that's used. And so, of course, you might have heard about the fuel versus food debate. And currently, much biomass, you know, if you get biofuels in your petrol mix, as we do, say from Brazilian sugarcane, it's competing with food production. In things like cornstarch or sugar beet, here in Europe, it's competing with food. Whereas lignocellulose biomass very much doesn't. It's about the woody part of the plant. It's about the bit that you discard when you make food. It can be also, as you see in the bottom right-hand corner here, a dedicated biofuel crop, and that's a willow plantation that you can see. It comes from the cell walls that we're interested in. You know, there are high-value products inside the cells of trees, but it's the cell walls that we're interested here, and we're interested in the cell wall components: cellulose, hemicellulose, and lignin. Cellulose is when the plant is very green, you're seeing the cellulose growth, and as it browns, you're seeing the lignin depositing upon that, and the hemicellulose is sort of the glue that holds them together. Here are the compounds. Cellulose is a sugary polymer, long chains of cellulose, which then hydrogen bond to make sheets, and then those sheets sit on top of each other to make three-dimensional structures. And then I want to draw your attention to lignin. Look at the beauty of this compound, the amount of functionality that is present in lignin. And you look at it, and in particular the aromatics, and you can see that you could make so many things from lignin. But I'm afraid that the thing that is said very much in the research area is you can make anything from lignin except money. And this is part of the problem. So when you think about the possible biomasses, so talk about that sugar biomass. You take the sugar, you ferment it, you make ethanol, or different processes, different simple chemicals, and you use them to make your various different products. You can take a starch, and relatively straightforwardly, you can hydrolyze it, you then ferment it, and then you can go on to make your products. In order to get to that stage with, I've got the example of softwood, but any wood would do here. In order to get to that stage with lignocellulosic biomass, you need to have some kind of pre-treatment that gets it to the stage it needs to get to before you do the hydrolysis, say, of the cellulose. And it's that pre-treatment that people can't do on the industrial scale necessary for the biorefinery. It is done for paper production, but paper production is a very high value product, and there's a great deal of waste generated in doing so, which is the lignin. And the lignin comes out in a form where all that's done with it is it's burned in order to fuel the paper production facility itself. And so we have worked upon, and indeed others, biomass deconstruction. And we use, as you heard, a particular group of liquids called ionic liquids. There are some examples of them there on the top left-hand side, but they are simply salts that are liquid at room temperature, and they have over this century slowly made the route from academic laboratory. The first industrial applications using ionic liquids were at BASF, into availability on a large scale, as you can see in the bottom picture on the left-hand side. And what we do there in our group is we do a delignification process. So we dissolve the lignin out of the wood. That leaves the sugary components for hydrolysis and development into products, sometimes as cellulose, sometimes as cellulose derivatives and simple molecules. So for your sugary component, but the important thing here is that we can recover the lignin in a form which is to some extent usable. There are problems around this. These are the challenges that need to be faced, but you can turn lignin again into a variety of small molecules, but unfortunately we haven't achieved a product mixture with less than 40 products in it in my laboratory, and so there are problems around purification of those small compounds. You can actually just dump out a lump of lignin and then do something like turn it into syngas through a pyrolysis process, and then use that syngas in a Fischer-Tropsch type process in order to generate compounds. Or you can use that lignin as a polymer itself, which is one of the things that we have a great deal of interest in at the moment. So replacing, and so the challenge before us is we need to make currently available materials. There are some things where we actually want the material that we have today, and we need to get it from these renewable sources. But actually for many things, and particularly for many of the things that polymers are used for, what we want is we want materials that have certain properties, but frankly we don't care what that material is. And so we want to make new materials from renewable resources that can match the properties of currently available materials. And of course, as we do that research, we will discover new materials that have properties that currently aren't available, and we will find uses for them. And so all of those things are the synthetic challenge that faces us over the next 20 or so years. And of course, all of the processes themselves must be sustainable. One of the things that people do is there is a kind of acting assumption, and you see it in the scientific literature again and again and again, that, oh, because something comes from a biological source, it must make a biodegradable plastic. And I've seen this again and again. And of course, you know, we have to think what we mean. Do we mean that actually, you know, we discard the plastic liberally wherever we do, and at some time scale, it will just, you know, rot down and biodegrade into the environment safely? And of course, that time scale becomes very important, because we have plenty of plastics that people think of as biodegradable, that if you did that, they would be present for hundreds of years. In fact, in order to biodegrade, they need to be composted in an industrial compost unit. And so we should really think more carefully about when we talk about biodegradable and when we talk about compostable, because many of the materials that we currently describe as biodegradable are in fact only compostable. And we need to think about this little matrix here. So the vast majority of conventional plastics are up in the left-hand side of this slide, and that they are both fossil-based and non-biodegradable. But also below that, you have fossil-based plastics that are biodegradable. The fact that it comes from fossil fuel does not mean something has to be non-biodegradable. And so we can have biodegradable but fossil-based. And of course, we can have the reverse. We can have bio-based but not biodegradable. So for instance, I have not seen a lignin that is truly biodegradable. And of course, the holy grail, if you like, biodegradable and bio-based. But only really in the most superficial way, the holy grail, because like I said, many materials, we want them to be durable. And so for durable materials, we don't want, you know, I don't want my garden furniture dissolving every time it rains. You know, so durable materials, we need to think about them, making them very durable, but also making them suitable for plastics recycling. And that's not just the material itself, that's the product. And there is a great deal of interest in the moment at designing things to be better recycled. But those things that can be biodegraded are far more suitable for those uses which are more about discardability. So packaging, cheap materials that are used once. And so we do have to think about this whole network and not just be trivial in our analysis. So with that, I'd just like to say thank you and ask if you have any questions.
Thank you very much, Tom. I just thought I can say to everyone, because I didn't have a chance at the beginning, if people want to pose questions, obviously you can add things on the chat, or you can raise your hand and I can come and unmute you if you want to ask a question. So, but thank you very much, Tom. There was a question in the chat, although from Gersh Ray, although he said that you probably have answered it already, about bioplastics like hemp plastic, whether they are gaining traction and what are the barriers to adoption. And I think you may have answered that, but I don't know whether you wanted to expand on that.
And so a bit, you know, the problems that I addressed, but also with hemp particularly, there's a problem of scale and cost. And it is about that initial part of the processing that adds to the cost, but also you get this kind of, is it chicken or egg? Do you need the scale to, you need the scale to bring the cost down, and so then make the products the ones that we wish to buy. On the other hand, without the scale, you can't get the cost, and so there is a bit of a chicken and egg problem around the adoption of these kinds of plastics as well.
Thank you very much. So if anyone else has another question, you can raise your hand and then I can unmute your microphone so you can post the question directly, or you can put something in the chat. Yeah. Okay. So, Tom, I just saw a question coming in from Jessica saying, do you reckon will we ever be able to fully eradicate the use of fossil fuels in plastic production, or will they always have a presence in plastic?
Oh, yes, we will be able to. No, so it's a matter of time scale. Of course, at some point, you know, getting fossil carbon out of the ground is just going to become prohibitively expensive, and it will stop. And I can't tell you the timescale of that because it's a very complex economic answer. So at some point, definitely yes. And of course, so I kind of liken it to actually the use of biomass to make carbon is a bit like wind power. You know, there's a tipping point happened a few years ago with wind power where that chicken and egg problem got solved and it dropped in price radically. And so now, you know, wind power isn't used because it's green, it's used because it's cheap. And that will absolutely happen with biomass-derived chemicals. At some point, as the research goes on, at some point it will become that the cost of generating the chemicals that we use and the materials that we use every day from biomass dips below that at which is the cost for taking it from oil. And at that point, the industry will swing.
Okay, thank you. There are some questions coming, so I'll just try and read them in the order they're coming in. So from Ed Stenmuller from the University of Sussex, he's asking whether are there advances in automated sorting of plastic waste streams?
Yes, there are. And so one of the lucky things about many of the plastics that we use in things like, you know, if you think about a drink bottle, you know, the vast majority of that bottle is PET, the bottle itself, but the cap is probably high-density polyethylene or possibly polypropylene. Fortunately, these materials have very different IR spectra, and so there are sorting machines where what happens is you scan the plastic. The first thing you do is you shred the plastic. You scan the plastics with an IR probe, and then you sort, you know, and actually they do it by air. They just, you know, they blow, because they're now tiny little chips, they're quite light. You blow the different plastics in different directions, so you have that kind of separation. Another one that's very useful with drinks bottles, and very lucky with drinks bottles, is that the density of PET is greater than the density of water, so it sinks, and the density of high-density polyethylene and polypropylene is less than that of water, so it floats. And so there are these, you see these flotation tanks which are used to separate chips of plastics. And so things are moving on, but the reality is the vast majority of plastics recycling is done by poor people by hand. And you know, we really do need to get automated processes that, again, can deliver these processes at a price that companies will actually do it. I mean, there is some place for legislation and regulation, but actually, you know, unfortunately, these things, you know, not unfortunately, that's just the fact of the matter. These things are very much driven by the economics of the situation. And so recycling is improving all the time. There are materials that are particular problems. So the polyester used in fabrics, you know, the polyester cotton blends, they are so intimately blended that even the kinds of separation that I've just talked about can't separate the cotton and the polyester. And so you need to find ways of being able to recycle what is a massively used fabric.
Thank you. There are quite a few questions in here. I'm going to go to Michael Walker, who raised the hand, so maybe getting tired of having the hand raised. And hi, Michael.
Hi.
Do you want to ask a question?
Hi, Tom. That was a fascinating talk, and I really appreciated your mentioning Anne Julian and Harry Kroto. I have very fond memories of being taught by Harry back at Sussex a long time ago, so it's nice to hear him being talked about again. You touched briefly on legislation, and I wondered if you would like to expand on whether regulations such as the banning of plastic microspheres in cosmetics and various other bits and pieces, are they a distraction, or is regulatory control a real driver in this area?
So I think there are, if we talk about regulatory control, first of all, on the global level. So in fact, I know through my Royal Science Chemistry activities, the UN at the moment is working on what they call in the strategic management of chemicals in the environment. And it is vital that we get some kind of global regulation in order to prevent rich countries dumping their waste on poor countries. And I think one of the important effects of that is that it will then drive innovation in the richer countries, because if what you can do is just dump it on someone else, what you do is you dump it on someone else. But when you can't do that anymore, then it forces you to think about how you're going to deal with these. But the specific things like microplastics, I think, a lot of the microplastics in the ocean don't come from microplastics. They come from conventional plastics that have ground down into small amounts. They do. It does have impact, and I think again, it's when the regulation is done in a way that its intention is to drive innovation, then I think it can be useful. And and what we're seeing at the moment is, I know of research projects, for instance, about making micro beads for cosmetics out of cellulose. And so there are ways in which I think the regulations can be used in a very positive way, because my feeling, I mean, you might say, I would say that because I'm a scientist, my feeling is that we are going to innovate our way out of this. And I'm confident, I think we will innovate our way out of this, but innovation doesn't happen in a vacuum, and regulation that is well crafted can actually drive innovation rather than just being seen as being a block.
Okay, thanks. Michael, did that answer the question?
That was an excellent answer to the question, that it's driving nice ideas around. That the global answer is that was. I couldn't have wished for a better answer to that question, Tom.
Thank you.
Good. Good. There are a few more in the chat there. Tom Collin asked, what would you say is the most promising area in terms of sustainable chemistry?
Oh God. How do I answer that question without offending one colleague or another? I think there's in different areas there are different things. So in my own world, the world of solvents, I think that there are huge advances to be made. In the world of catalysis, at the moment, so catalysis has got to the stage now where actually, do you know what? There are lots and lots and lots of things that we can, and probably in terms of the need to generate any particular compound, we have there is a way of making any compound if you can draw it, you can make it. But what I think the real challenge is now becoming is a lot of that chemistry depends upon elements that would be colored red in that periodic table that I showed you, and the drive to being able to have the range of reactions that we have available, but using elements that would be green on that periodic table is a really important challenge.
Okay, thank you. Another question from Jessica, which I think is linking to some things you said before. Says, so therefore, will you say that biomass will be the way to go, which links to the question you just answered about which areas are most promising?
again, I think biomass will be very important so I can imagine a world in which every car is powered by a battery, for instance. So whether biomass becomes the answer to fuel or not, don't know. And actually, I also think there's never been any point in history where humans have depended on a single source of energy. What makes us think that there'll be some point in the future where we do? It'll be horses for courses with all the different names. But I could imagine every car and every truck being driven by a battery-driven motor rather than petrol. But there are some things that have to be made out of carbon. My shirt, it can't be made out of a battery. It might be made into a battery, but it can't be made out of a battery. It needs carbon. And there are things that we need carbon for. And then you'd say, well, where will that carbon come from? And you think, well, the options are it comes from, fossil fuel says the word. It does come from biomass, just fossilized biomass, or it comes from currently living biomass. And so I think that absolutely we will always need a source of carbon. And if we don't want it to be something we dig out of the ground, it better be something we grow out of the ground.
Okay. Another question from Katie Dick. She asked, and I think it's linked to the question that Michael asked as well. What role do you see for government in supporting sustainable chemistry? I know you kind of answered that, but maybe to add.
But it is that. It's about being an enabler and driver of innovation. It is also about, there's a lot of the very innovative chemistry that is reaching into industry is doing so by, small, medium-sized enterprises, spin-out companies from universities. These kinds of operations cannot operate without some kind of support. And that doesn't mean, necessarily, government giving them money, but it does mean that government has a role to play in understanding the environments in which these kinds of companies can thrive. And actually, over the summer, the RSC did a report on the chemical workforce across the UK. And one of the things that it showed was that you get these hotspots of SMEs where once a certain number of them seem to get to an area, there's a cluster that forms around them and they're attracted to each other. Governments, both national and regional, need to look at that kind of stuff and say, okay, how can we stimulate this across the country and indeed the world?
Okay, I would say there's another couple of questions. So I would say at this point, I will read them if that's okay with you, Tom, and we'll answer them. But I would just ask that there are no more questions after that, just so we keep it within the time, because I just want to make sure that we respond to the ones that are here. Is that okay, Tom?
That's fine by me.
So Audrey Pearson asked, while polymer materials are one part of the equation, plastic additives, for example, flame retardants, dyes, plasticizers, etc., are on the other side. Do you have any thoughts on sustainable replacement options for these?
Yeah, it's not part of my own work, but lots of people are looking at completely new kinds of plasticizers. Again, bio-derived plasticizers, potentially biodegradable plasticizers. Why has my screen just gone off?
Oh,
it's all right. It's just my screen. It's not. You're still here.
Yeah.
I needed to move. I think it's such a long time since I moved my mouse that the screen went off. So people are looking very intensely at those additives. Which the thing about plastics is that, of course, as I say, since the Blue Planet, they have very much come to the public's attention, and part of the reason for that is, of course, you can see them, and what we know as chemists, that when you see that the ocean currents are taking these plastics to Pitcairn Islands, we know that they are taking a whole load of chemicals that you can't see, and that those chemicals are every bit as much of concern to us as the plastic material itself. And so, yeah, people are working on those things.
Okay, and I think this will be the final question from Harry Parr. There's a comment after that, but it's not so much a question. So given the confusion between compostable and biodegradable, as well as what is recyclable on a local scale, do you know if there are any plans for changing the way this is communicated in the future?
No, that I don't know. It's certainly something, well, I suppose we, the RSC, will, we will try to rise to that challenge. And it's that thing that, well, it's that thing that we see in the current situation with the pandemic, isn't it? That words take on meanings and are used in particular ways, by a non-expert, of course, public. And it is once certain words have come into the public arena, it is very, very difficult to tweak these meanings in these kinds of ways. It is a huge challenge. There's an educational challenge in it, but I do not see the immediate solution to that. But it is, I can tell you, it's absolutely one that the RSC is looking at to try and get enough information out into the public in a way that is usable by the public so that they can recognize the differences between these things. But it is a huge problem. Yeah, I say the word biodegradable, and even as a chemist, I think, oh, that means I can chuck this away and it'll just rot in the hedge that I've just thrown it in. But of course not. That is not what that means. And you can't do that. And the vast majority of things that are labeled as biodegradable would not meet my simple concept of what I would expect that word to mean. I mean, I guess there might be a thing in regulation of a kind of ban, that certain things which we currently call biodegradable, we cease to be allowed to call biodegradable.
That's very interesting. Thank you very much. There's a final comment from Joseph Senia about his PhD research. I don't know whether you can actually see the chat there.
Let's have a look. I can see the chat.
The last comment, and I'm just saying because probably I will make a mess if I want to read that, so you might want to.
Right,
It's the last.
On the use of lignocellulosic biomass waste materials. Oh, fungal solids, yeah. Yeah, the use. So fungi are really, really interesting in this regard, because one of the things about lignocellulose, of course, is it has evolved to be resistant to chemical attack. Trees do not dissolve when it rains. And so it's really, really intractable. And actually, fungi in general are what many, I mean, certainly my biological scientist friends and colleagues are extraordinarily interested in, because they have got that trick of being able to break down if you walk through, just a wood, you will see that, wood that has fallen, trees that have fallen, absolutely covered in fungi that are digesting it. And so, so bioprocessing with fungi and fungi-derived materials is a hot topic.
Okay, well, Professor Wilson, thank you so much. Julian, you want to say final words?
Just a few final words, because I'm conscious of time, but I did want to take the opportunity to thank Tom for a real food for thought, and possibly quite a pointed reminder about consumerism in the broadest sense. But I think that does come back to some of the comments that you made, Tom, about the need for information, education, whatever you want to call it. And you alluded to not only the pragmatic regulation that, if done in the right way, can drive innovation, but also I think we've seen that consumer choice and demand can also drive government thinking that might end up driving regulation and innovation. So it's very much an end-to-end thinking that's required here in much the same way as you've described how we need to think about these types of chemical materials going forwards. So it's left us with some thoughts pre-Christmas and on the wrapping paper, etc., that we're going to throw straight into the bin. But nonetheless, maybe it'll make us all challenge a little bit and question the sources of some of the product materials that we use and how and when we do recycle them, at least as it currently stands at the moment. So thank you very much indeed for your time and for your thoughts. And it just really remains for me to wish everybody as good a Christmas as they can possibly have under the conditions that we find ourselves in this.
Stay safe and well, everyone.
Absolutely. Thank you very much indeed. Goodbye.
Thank you.
Thank you, everyone. Just in case it's not clear for everyone how to leave the session, you can click on the X cross at the top right-hand corner, and that will leave you. I'm going to unmute you also if you want to clap to say thank you to Tom, then you'll be able to as you are leaving their session. It may get a bit noisy though. Thank you.